Good evening and welcome back to Sense of Science. Today we are going to be doing the topic Galvanic Cell. This is a topic which is used in class 11 redox reactions and carries on directly to class 12 as it is in the chapter of electrochemistry, and definitely it's expected that we get one or two questions from this in the boards as well. Okay, it's a very simple and interesting topic, so let's try to understand what it is. Now if I talk about a galvanic cell actually is a cell. You all know what a cell is, an electronic device, an electronical application, the cell which converts chemical energy of a redox reaction to electricity or electrical energy. This is my galvanic cell. A cell or a device which is converting chemical energy of a redox reaction to generate electricity is my galvanic cell. Alright. Now, the important terms which I have in this definition are chemical energy to electrical energy, that means to generate electricity by chemical energy by a redox reaction. This is very important, by a redox reaction. So before moving on to the details of galvanic cell, I'll just give you a recap. What is a redox reaction? A redox reaction is a reaction in which there is simultaneous oxidation and simultaneous reduction. So redox stands for simultaneous reduction and simultaneous oxidation. Now, if we are talking about generation of current, which is the aim of galvanic cell, current can only be generated when electrons are flowing. The flow of electron constitutes electric current. So when I am talking about this from a galvanic cell, that means I have to carry out such a redox reaction which will generate current. That means a redox reaction which will make electrons flow. Isn't it? So what I do is I carry out the redox reaction in such a way that the electrons flow from one terminal of the cell to another terminal of the cell. Alright. Now as you all should know from class 11 redox reactions, in oxidation we have a loss of electrons. Electrons are lost in case of oxidation, whereas when we talk about reduction it is the opposite and we have gain of electrons. Okay, this loss and gain of electrons are a typical characteristic of the redox reaction which you must have learned by now. Okay, so what I can see is if one terminal from this, the information if I infer, if one terminal loses the electron where oxidation is happening, and these electrons from the lost oxidation terminal go on to the terminal where I have reduction, where I want to gain electron, the electrons can flow there, and if electron is flowing, of course current will flow. This is the base of the galvanic cell, that on one terminal or one electrode of the galvanic cell, a cell is made up of electrodes, I would have oxidation where electrons would be lost, and simultaneously on the other terminal I would have reduction where electrons are gained. So that would actually constitute a flow of electrons, and which will actually lead to current generation, which is my aim of galvanic cell. Now one more term before we begin with the construction of the galvanic cell is that the redox reaction which is happening in the galvanic cell is called indirect redox reaction. Why indirect? Because it is happening in two different terminals. The oxidation is happening in one different terminal or one different electrode, and reduction in the other one. That's why it is called an indirect redox reaction. Okay, this is to be more precise and specific. If you write a redox reaction also, it's absolutely correct. Okay, so now let's begin with the construction of the galvanic cell. Construction. Okay. Now, for the galvanic cell to be made, I'll just erase this word so that I can get a little more space. For a galvanic cell, there are two terminals as I had told you. This is my terminal 1 or my electrode 1 is a beaker, and similarly electrode 2 is also a beaker. Okay. In the first electrode, which is on left side, this becomes your anode, the left terminal we take always as an anode. This is our convention. And the right side becomes your cathode. Okay, this is a convention. Okay, there is no logic. We are conveniently doing this. Left as anode, right as cathode. In anode, what I have is a metal which will lose electrons, and in cathode I have a metal which is able to gain electrons. Now, simply saying in simpler terms, in the anode, just listen to this for a minute. In the anode, I have a more reactive species, and in the cathode, I have a less reactive species. This will lose the electron and this will gain the electron. Okay. So if I take a look at the metal reactivity series, I can take the easiest example for this galvanic cell. On the anode, let me take up zinc, and on the cathode, let me take up copper. I can take up anything. Okay, one more reactive and one less reactive, so the reaction takes place. Okay, I can take up anything actually. So I am taking the most convenient and easy one. That is, on the anode I have zinc, and on the cathode I have a strip of copper. So let's take that as our base. On the anode I have the silvery white strip of zinc. Okay, this is my zinc. So I can write this as my zinc, which is more reactive. And on the cathode I have the reddish brown copper. So I can just take a look for the brown color. No, it's not available, so we'll take up the red color only. So this is my strip of copper. Okay, so this is your copper. Okay, now for a cell to react, of course a circuit has to be complete, and whenever I have two electrodes, I need an electrolyte, which is a salt solution of the metal, for the charges to flow, because charge will only flow in the case of electrolyte, in the molten state or the aqueous state. In the solid state they won't be conducting. So what I can write is, I will take the salt solution here. So for the first one, in case of zinc, I take the salt solution as zinc sulfate. We can take any salt solution, I repeat, but for convenience sake of the question, I am taking up zinc sulfate. So I have zinc sulfate here, which I am taking for my convenience. Okay. So this is your zinc sulfate, and I take this as 1 molar. Okay, in the standard conditions, we take the galvanic cell always in the standard conditions, and standard conditions for concentration is 1 molar. That means 1 mole per liter. Okay, and in the same way, for copper, the electrolyte will be your blue copper sulfate. Okay, so this is copper sulfate aqueous, again 1 molar. To become standard in conditions, I take the reaction at room temperature. So the temperature for this reaction becomes 298 Kelvin or 25 degree Celsius. Okay, this becomes 25 degrees Celsius or 298 Kelvin is the standard temperature I am taking here. Is that fine? Now for the circuit to be completed, I am connecting this to a switch and a voltmeter or an ammeter, which will detect the current or potential difference. Any electrical device which will detect the current or potential difference will be taken up for this purpose. So I am completing the circuit with wires, and in between wires I have a voltmeter. So here I have a voltmeter, and also I have a switch which is closed for circuit to conduct. Okay. But what I will find, actually, this circuit is still not complete. The circuit is not complete at all. It is still open at one end. So for the circuit to get completed, I use something else which is called as a salt bridge. Okay. Now salt bridge is constructed somewhat like this. So just take a look at this. It's like a tube actually, which is going from one terminal to the other terminal. A simple tube is your salt bridge. You can draw it as a freehand tube. There is no need for perfection here. Okay. Now what the green shade which I have given here actually is a gel like substance which is there in a salt bridge, like agar agar. Now agar agar is a gel like substance. Agar agar, which is a gel like substance. Now why do I use agar agar here? The main reason for using this substance is that this will hold the salt properly, otherwise the salt would fall from the open ends of the salt bridge. So the agar agar would hold a salt in it, and the salt which I will use here is inert salt which is non-reactive, so that it does not change the reaction at all. Okay, so I use inert salt which is non-reactive, so that it will not change the course of the reaction. Is that fine? This is my construction of the galvanic cell, in which I have two electrodes, the anode, which is the left terminal, and cathode, the right terminal. In anode I have a strip of more reactive metal like zinc. In cathode I have a strip of less reactive metal like copper. Okay, and this is joined with the help of wires and a voltmeter for detecting current. But to complete the circuit, as the circuit is initially not complete, I have a construction called a salt bridge, which is a tube containing a gel like substance like agar agar in it, which holds a salt it has. The functions of the salt bridge we will be discussing in our next video, which will be the functioning of a galvanic cell. Okay, so the functioning of galvanic cell will be discussed in our next video. Fine, stay safe and please like, share and subscribe my channel. Thank you.